We are now going to continue looking at the structures of muscle fibers. So the PC stores of these muscle fibers will differ, and the PC stores, PC stands for phosphocreatine stores, and the phosphocreatine stores. So phosphocreatine is high energy phosphates, and they last for a very short time. So in slow oxidative muscle fibers, since they're working aerobically for a very long time, obviously they're not going to have many of these, as these are the PCs. Phosphocreatines are very short lasting. So, and since the slow oxidative muscle fibers are long lasting, that means the PC stores of inside the slow oxidative muscle fibers are going to be very low. However, in fast oxidative glycolytic muscle fibers, the PC stores are going to be quite high, because the fast oxidative glycolytic muscle fibers can work anaerobically. And if it can work anaerobically, it means it can work for a short period of time, but at a high intensity. And that is what these phosphocreatines are doing, working at a very high intensity that lasts for a very short time. So a FOG muscle fiber would have a high PC store. This would be similar in a fast glycolytic muscle fiber, as it's also working anaerobically, and so we need that high energy, the high energy of the phosphocreatine. So we need those high energy phosphates, and also fast glycolytic muscle fibers also last for a very short time. So the PC stores in a fast glycolytic muscle fiber would also be very high. Now, the glycogen stores in a slow oxidative muscle fiber, that would be relatively low, because glycogen can be broken down to make glucose, and glucose is only used in anaerobic respiration, as the glucose is the reactants and lactic acid is the products, and that produces energy. So if the slow oxidative muscle fibers only work aerobically, that means they have no need for glucose to produce energy. So the glycogen stores of a slow oxidative muscle fiber would be very low. In a FOG muscle fiber, the glycogen stores would be relatively high, as it is working, or it can work anaerobically. So would need to have glycogen stores to then break them down into glucose to transfer into energy, as it would work anaerobically. This is similar in a fast glycolytic muscle fiber, as that also works anaerobically, so would also require glycogen stores for glycogen to be broken down into glucose to make energy, and for the muscle fiber to, well, work. Triglycerides are these storage molecules, and these, as slow oxidative muscle fibers depend on oxygen, that means they can only undergo aerobic processes. And since slow oxidative muscle fibers work aerobically, they use these triglyceride stores, and these triglycerides are energy stores which can create ATP through beta oxidation. And so as triglyceride stores are dependent on oxygen, as it's a aerobic um, reaction effectively. That means there's a high amount in the slow oxidative muscle fibers, because this links to slow oxidative working aerobically and the high number of capillaries supplying the oxygen. That means there can be a high amount of triglyceride stores. Now, in FOG muscle fibers, the triglyceride stores would be less than slow oxidative, but still relatively high. So a sort of medium amount, as they can still work aerobically and still have a reasonable number of capillaries go into each FOG muscle fiber. So we'll still have a relatively high triglyceride stores, but obviously not as high as the slow oxidative, as the slow oxidative primarily or just focuses on aerobic respiration, whereas the FOG muscle fibers can work both aerobically and anaerobically. And finally, the fast glycolytic muscle fibers would have a very low triglyceride stores, as they don't work aerobically. They just work anaerobically. So don't use these aerobic processes to store these triglycerides. Now, aerobic enzymes. We know that slow oxidative muscle fibers work aerobically through aerobic respiration. So it's obviously that it's clear that there would be a high amount of aerobic enzymes in slow oxidative, as it just works aerobically. In FOG muscle fibers, there would be a medium amount of aerobic enzymes, as it can work both aerobically and anaerobically. So would still need those aerobic enzymes to function when it wants to function aerobically. So is similar to slow oxidative like that, but isn't similar due to the fact that there's a less amount of aerobic enzymes. Fast glycolytic muscle fibers, there is a very low amount of aerobic enzymes, as the muscle fiber works anaerobically, so has no need for the aerobic enzymes as it's not going to use them. Now, opposite to that would be the anaerobic enzymes. So it makes sense that since the slow oxidative muscle fibers had a high amount of aerobic enzymes, that means they'd have a low amount of anaerobic enzymes, because they're working aerobically, so don't require the use of anaerobic enzymes. FOG muscle fibers, however, have a high amount of anaerobic enzymes, as we know it can work aerobically, but predominantly it wants to work, or it does work anaerobically. So there would be a high amount of anaerobic enzymes, so it can work anaerobically to the best of its abilities, to the highest potential it has. And also, similar to this is the fast glycolytic muscle fibers, as this muscle fiber just works anaerobically, so would need a high amount of anaerobic enzymes to be able to function anaerobically. And finally, the myosin ATPase content. So the myosin ATPase activity is effectively this enzyme known as myosin ATPase breaking down one phosphate bond in the ATP, as there are 3 phosphate bonds in ATP, and it breaks that bond down to create a DP, and an inorganic phosphate. So in slow oxidative muscle fibers, since there's a slow contraction speed as it works slowly but for a long period of time, that means that there would be a low myosin ATPase activity and therefore a low myosin ATPase content, as it's working slowly, so it doesn't require fast process of breaking down that ATP into ADP and an inorganic phosphate. In fast oxidative glycolytic muscle fibers, the myosin ATPase activity or content would be at a much higher amount compared to the slow oxidative, as that works much quicker than the slow oxidative, so has a much faster contraction speed than the slow oxidative muscle fiber, so requires a higher activity of this myosin ATPase breaking down that ATP. So the myosin ATPase content of the fast oxidative glycolytic muscle fiber would be much higher than the slow oxidative. The fast glycolytic muscle fiber would also be higher than the FOG muscle fiber type, as the fast glycolytic muscle fiber is working at the fastest. It has the fastest contraction speed out of all three, so would need to be able to break that bond down, that ATP down as fast as possible, so it can contract as fast as possible. Therefore, there'll be a very high activity rate in there for the myosin ATPase, and therefore would be a very high myosin ATPase content, which would be higher than the FOG muscle fiber type. I'm going to stop the video there, and the next video we will look at the types of muscle fibers, but the function of them this time.